So in this lesson, we're going to add two new tools to our stoichiometry toolbox. We're going to be learning how to convert between the number of particles and the number of moles, and between the volume of a gas and the number of moles. But first, let's review some of the things we learned in previous lessons. So the homework problem was, if 200 kilograms of butane is burned and 150 kilograms of carbon dioxide is collected, what's the percent yield? Well, we need to know what butane is in terms of a formula, because that's going to be important here. So let's look at that first, butane. See, butane, the prefix but means 4 carbons in a chain. The suffix ane means all single bonds between those carbons. So 1, 2, 3, 4 carbons in a chain, all single bonds. Each carbon must have 4 bonds to complete its valence energy level, electron energy level. So I'm going to need 3 hydrogens on the end carbons. That gives us 1, 2, 3, 4 bonds. And the middle carbons already have 2 bonds, so they only need 2 hydrogens. And so butane's molecular formula, simple molecular formula, is C4H10. Okay? Complete skeletal formula, or complete structural formula is here, molecular formula here. And so this will include in our balanced chemical equation. If we're going from one species to another, in this case we're going from butane to carbon dioxide, we have to have a balanced equation, because anytime you go through from one species to another, you have to have a molar ratio. Molar ratios come from balanced equations. And that leaves me breathless saying all of that. All right, we said that carbon chains of less than 5 or fewer carbons in a chain we're going to consider to be a gas at room temperature and pressure. And we're going to react that with oxygen, because that's what you're doing when you're burning things. And anytime you're reacting a hydrocarbon and oxygen, you always, in this class at least, are going to assume that you're going to get CO2 and H2O. Those are the products every time. And water is going to be a gas because of the heat involved. We're burning stuff. We want to list all of our elements in an atom inventory. Make a kind of a grid here, or mini spreadsheet, I suppose. And we're going to use this to write an atom inventory to keep up with all of our atoms on both sides, so we can easily balance the equation. We're going to start with 4 carbons on the left, 10 hydrogens on the left, and 2 oxygens on the left. And on the right side, we're going to have 1 carbon, 2 hydrogens, and 2 plus 1 are 3 oxygens. In order to balance the equation, we cannot touch these formulas now. Once the formulas are set, you must leave them alone. Once the formulas are set, you must leave them alone. So, we can only use coefficients in front of the formulas to change the number of atoms in the equation to balance everything out. And then we'll be we'll have an equation that represents reality in terms of what law of conservation of mass and the atomic theory and so forth tell us. Now, if I have 4 carbons on the left and I need 4 carbons on the right, I'll put a coefficient 4 here. That's going to change the number of carbons and oxygens. So that means we now have 4 carbons, which is what we're looking for, but we also have 4 times 2, that's 8 oxygens here, plus the 1 over here. So right now we have 9 oxygens. All right. We always want to balance oxygen last and hydrogen next to last. We've got the carbons balanced, so we're ready to balance hydrogen. I've got 10 on the left, only 2 on the right, so a coefficient 5 in front of the species that contains the hydrogen will get us up to 10 hydrogens, but it's also going to change the number of oxygens. And now we have 4 times 2 or 8 oxygens here, plus 5 times 1 or 5 here, so that's 13 oxygens that we have at the moment. Alright, so what we have here is that case we sometimes get. We have an odd number of oxygens on one side and an even number on the other side. We're going to go through and multiply everything by 2. So I have a coefficient 1 here. I'll make that a 2. I'm not going to bother with the one in front of oxygen right now, because that's the one we're trying to fix. I'm going to change this 4 to an 8 and this 5 to a 10. And go through and recount everything. We're changing the number of carbons and hydrogens on this side. We now have 8 and 20. I've multiplied everything over here by 2. So if I've done it right, I can check and see I've got 8 carbons here. And I've got 8 times 2 or 16 oxygens on this right here in this part of the formula, or the equation rather. And then 10 over here. 10 times 1 is 10. That gives me 26 oxygens to the right. So I'm going to put 26 here. And I didn't change this to 20. So now that I can see that I've got an even number of oxygens on this side, getting the right number of oxygens on this side is fairly easy. I put a coefficient of 13 in front of that species, changing the number of oxygens to 26. Okay? Alright, now we have a balanced equation. We are ready to start working on the stoichiometry. We're starting with 200.0 kilograms of butane. So 200.0 kilograms of C4H10. And we'll put that over 1. Most of the time with stoichiometry, you can start with your starting amount over 1. Then we want to convert it into moles, but a molar mass comes in grams and moles. So we have to convert kilograms into grams to use that. So we know that 1 kilogram equals 1,000 grams. Okay? Every conversion unit implies an equality statement, and actually the conversion unit is actually built from something that's equal. So it's a good idea because, where am I from? Missouri, thank you. Only one person said that. I can't believe it. At this point in the semester, only one person saying that. You got to show me this stuff so I know what you're doing and know whether you're right or wrong. Show me this stuff. 1 kilogram equals 1,000 grams. Now I'm going to count it off if you don't have that. But if you didn't know how to convert from grams to kilograms accurately, you would have a problem getting the correct answer here. So that allows me to cancel kilograms. And so what I have now is, doing this math, I'm going to have the number of butane, the grams of, or the mass of butane into grams. And now I'm ready to use molar mass to convert to moles. To calculate molar mass, we're going to take the atomic mass of carbon and oxygen, which comes in atomic mass units, and we symbolize that as the lowercase letter u, but we're not going to worry about that here because for finding molar mass, we're going to be using units of grams for all this. So on your periodic table, in class preparing for AP Chemistry, we're going to use the periodic table that's used for AP Chemistry, and the atomic mass here is 12.01. Oh yeah, it should be hydrogen, shouldn't it? You're right. Should be hydrogen. Hopefully I would have noticed that in a second. Okay, so let's see. Hydrogen's atomic mass on that periodic table is 1.008. We have, let's see, in the formula 4 carbons, which is 48.04. And this is times 10, so that's 10.08. And so let's put this down here as being hydrogen. Make sure we list that properly. Add them together. 58.12. That's grams of butane, C4H10, equals 1 mole of C4H10. There's no reason to round anything off over here because I don't have any empty slots. But this equality statement now is what I need to build a conversion unit, just like I used this equality statement to build that conversion unit. I want to match the units and species that I have on the top here. I've got this species and this units. I want that on the bottom in this step. And the other side of the equality statement is going to go on the top, 1 mole of C4H10. Okay, and we're going to cancel units of grams. I'm going to cancel the species. Okay, so it's not necessary to have your species or even your units right next door to cancel them, just as long as they're in the problem when we set it up this way. All right, now we're ready to use the molar ratio. The molar ratio comes from the balanced equation. So these coefficients in front of each of these chemical species can represent single formula units, or we can multiply it by Avogadro's number and we got moles. Okay, it's still the same ratios. So 2 moles, 13 moles, 8 moles, and 10 moles still represents what's going on in the equation. So on the bottom then we want to have the 2 moles of butane, 2 moles of butane. Now on the top we want to get the CO2, so that's 8 moles of CO2. Cancel the units. And we're ready to convert this now to grams, because we want to answer in grams, or actually we really want to answer a final answer in kilograms. So we need the molar mass of carbon dioxide. Carbon's atomic mass is 12.01 atomic mass units, or just the lowercase letter u. We only have 1 carbon in the formula, CO2. Oxygen is 16.00 atomic mass units, which we symbolize with the lowercase letter u. So 12.01, and then 16 times 2 is 32.00. We get 44.01, and that's grams of CO2. So for molar mass, it's not AMUs, it's grams, equals 1 mole of CO2. Have an equality statement, we can build a conversion unit. 44.01 grams of CO2, 1 mole of CO2. So this is a conversion unit because the 2 parts, the top and bottom part, are equal to each other, and that means the value of this fraction is actually 1, and so what we're doing is converting to a different unit of measurement and not actually converting or changing the amount we have here. Right, cancel out moles, cancel out CO2, and we really need to get our answer into kilograms, because the problem gives you your actual yield in kilograms, and you can't cancel units to calculate your percentage yield unless this answers in kilograms. So we want to convert back to kilograms here. So I'm going to put 1,000 grams on the bottom now from this equality statement, and 1 kilogram on the top, which allows me now to cancel grams and leave me with kilograms of CO2. All right. Let's see here. And I get 605.7811, 425 kilograms of CO2. I'm going to round that off to match excuse me. I'm going to round this off to match the measured or calculated numbers, as this one, and this one, measured or calculated numbers that have the least number of digits. Well, all of these have 4 significant digits, so we want our final answer in 4. So 605.8 kilograms of CO2 is the theoretical yield. Okay, this is the theoretical yield. We're going to find the percentage yield by taking the actual yield in the problem. I gave you 150.0 kilograms of carbon dioxide collected. So 150.0 kilograms of carbon dioxide, and put it over this theoretical yield, 605.8 kilograms of CO2. Do that division, multiply by 100. Notice that the units of measurement are going to cancel. If you've set up your percentage calculations properly, you should always cancel units. In this case, we're also canceling species, but sometimes in percentages you don't always cancel species, depending on the kind of percentages you're doing. But for percentage yields, you always are going to cancel or end up canceling the species. All right, I get 24.76. percent I have 4 significant digits in both these numbers in the problem, so 4 significant digits here, underlining everything else and drawing an arrow, and I get 24.76% yield in or of CO2. Okay? All right. Well, we've done this enough for you to know that when you add up all the important stuff in here, okay, we're including coefficients, formulas, physical states, operators like this plus sign and this arrow here. When you add all these things up that are necessary, you get a value that's worth 15 points for just the balanced equation. Okay? When you add up all the things that are necessary for the atom inventory, it's worth 21 points. Now let me say something about this because as far as I know, I remember this is the first time we've come up to a situation where we've found an answer and then cancel that answer to find a final answer, at least in terms of coming up with points on this. I'm only counting this number, canceling this first number, and this final number 8 here. I'm not counting the stuff in the middle because there's really more than one way to get there. You should always have the same starting number. You should always have canceled that starting number in order to get to a final number. So this number, canceling it, and that number are all being counted for points, okay? But not the 4 and canceled, the 10 canceled, 9 and 13 canceled. All right, so that's worth 21 points. When I added up all the points for the stoichiometry, that's all the numbers, units of measurement, species, and canceling. I'm going to have come up with a total of 48 points. Now let me say something about that. It doesn't matter whether they convert the kilograms here and here, or they converted it somewhere else. Okay? They could have written their mass for the atomic mass is 58.12 grams and converted that to kilograms. As long as they convert to kilograms, that's all that really matters. And I'm just counting this whole thing right here as 1 point. Okay? And getting their final answer into kilograms, I gave 1 point. So where they do it doesn't matter, just so long as it gets done. Does that make sense? Yes? No, we're going to be doing more stoichiometry today and different types of stoichiometry. Okay? And then when I counted up all the things that are important, element, atomic mass, operators like this, times 4 and so forth, add all those up, I get 19 points for this molar mass calculation, 19 points for this molar mass calculation, and when I can't add it up everything that's important with the percentage yield, which means the actual yield, the proper theoretical yield, units of measurement, and species all cancel times 100, all the operators, underlining, arrows, everything that's important, this is worth 19 points. And you've done this enough to know what I consider to be important. All the cancellations and underlinings and arrows are all very important here, okay? When you add everything up for all this whole problem, we get a total of 141 points. All right? Up to now, all the stoichiometry problems we've done were mass-to-mass stoichiometry. Today we're going to talk about other kinds of conversions from particle to mass and mass to particles, and from volume to mass and mass to volume, at least for gases. Let's start with particles. So we're looking to convert particle to mass and back again. Okay? So the conversion for particle to mass is Avogadro's number. Now, Avogadro didn't come up with a number. He came up with a theory underlying the process, and other scientists later on figured out the number of particles in a mole. Okay? And the number is 6.022 times 10 to the 23rd power particles of anything. And it could be literally anything. But most of the time in a high school chemistry class, the kind of particles we're dealing with will be atoms or formula units or molecules or something like that. Okay? So 6.02 times 10 to the 23rd molecules of water is equal to 1 mole of water, for example. Or 6.02 times 10 to the 23rd sulfate ions is equal to 1 mole of sulfate ions, for example. Okay? So 6.022 times 10 to the 23rd particles of anything is equal to 1 mole of that thing. Okay? So here's an example of a problem that's going to use this concept. Two grams of hydrogen gas is reacted with oxygen from the air. So there's going to be plenty of oxygen here. We don't have to figure out what a limiting reactant is in this problem because there's more than enough oxygen in the air to react with a very small amount of hydrogen. So oxygen in the air, question is how many water molecules will be formed? Okay. So I'm going to walk you through the solution to this problem, and I'll give you a practice problem to work on, okay? So the first thing we want to do, and it doesn't have to be the first thing, but the first thing I like to do is to write a balanced equation. I can see from this question that I'm going from one chemical species to another, and the only way you can go from one chemical species to another is to have a molar ratio. And the only way to get a proper molar ratio is to write a balanced equation. So I'm doing hydrogen gas, and here's what you need to know about hydrogen gas. Hydrogen is one of the diatomic gases. The diatomic gases are hydrogen, nitrogen, oxygen, fluorine, and chlorine. Whenever you see those written by themselves, like they might appear in the environment, not dissolved in water as an ion, but appearing in the environment as by itself, you're going to have a diatomic molecule, H2, as Andrew noted. Okay, it's H2, and it is a gas. Okay? Can I list them again? Hydrogen, oxygen, nitrogen, fluorine, and chlorine. I haven't listed iodine. Iodine is kind of a special case. Iodine actually sublimates at room temperature and pressure, meaning it goes directly from being a solid to a gas at room temperature and pressure. When it's in a gaseous form, iodine is also diatomic. Okay? Bromine is usually a liquid at room temperature and pressure, but it's also diatomic. It's a diatomic liquid. But I didn't ask you to know those things. I only asked you to know hydrogen, oxygen, nitrogen, fluorine, and chlorine. Okay? All right. So H2, we're going to react it with oxygen, and it's also, as I said, one of those diatomic gases. So it's O2 and the gas. And we're going to react that together to make water, and we all know that's H2O, I hope. We could list it as a gas because technically there is a lot of heat generated here, but I didn't ask you guys to know about combustion for things other than hydrocarbons, so we can still call this a liquid. It won't affect much anyway. All right? So, and in fact, if you're reacting hydrogen and oxygen in a controlled environment, like a hydrogen fuel cell reaction to create electricity to run a car, you're going to get water in liquid form. So let's do our atom inventory now. We're going to list all the atoms in the equation. Make this kind of grid here for our atom inventory so we can keep up with everything. I can see I've got 2 hydrogens, 2 oxygens on the left, and 2 hydrogens and 1 oxygen on the right. To get everything balanced, I'm going to put the coefficient 2 in front of the species that contains the oxygen. That's going to change the number of hydrogens and oxygens. And now I'm going to have 4 hydrogens and 2 oxygens. And I go back over to the left to get the hydrogens balance, and I'll put a 2 here, and that's going to give me 4 hydrogens on the left, and that balances everything. Okay? So we have a balanced chemical equation now. Now we're ready to do the stoichiometry. We're going to start with 2 grams of hydrogen over 1. Almost all the stoichiometry we're going to do in this class, you can start with your starting amounts over 1. It kind of makes it easier to set everything up. And we're going to convert those grams into moles. So we have to have molar mass calculated. So hydrogen is, on the periodic table we use in this particular class, the atomic mass is 1.008. Other classes may use a different periodic table that has a different atomic mass listed on it, but for this class it's 1.008. And that's grams of hydrogen. Actually, I need to multiply that by 2, don't I? Duh. Okay. To quote Homer Simpson. So that's times 2, so that's 2.016, and there's nothing else in the formula, so we don't have to do any addition or anything there. We just say that's grams of H2 equals 1 mole of H2. I want to build a conversion unit here, and when I have 2 things that are equal, like these 2 things here are equal, if I put one of these 2 parts on the top and the other part on the bottom, the fraction actually equals 1, has a value of 1, so we're going to use that to convert how we're measuring this stuff without changing the amount. So the grams of hydrogen from the equality statement go on the bottom, and this allows us to cancel grams in hydrogen and give us moles when we're done. We're going to put 1 mole of H2 on the top, and then like we do with algebra, when you have x's and y's on the top and bottom of fractions like this, we can cancel these out. Now we're ready to use that balanced equation to convert from moles of H2 to moles of H2O. We're going to use the coefficients in front of the chemical species. These coefficients can represent the actual number of formula units or the number of moles in the equation. And so we're going to use 2 moles H2 here and 2 moles of H2O on the top, which allows us to cancel moles of H2. And since we now have moles of H2O, we're ready to calculate the final answer, how much H2O is going to be made. But this problem isn't asking for H2O in mass. Everything we've done so far and all the problems we've done so far, we would have calculated the molar mass and found the mass of H2O. But this problem doesn't ask for the mass of H2O. It asks for the number of water molecules. How many water molecules are formed. Okay? And the equality statement for that is 6.022 times 10 to the 23rd molecules of H2O equal 1 mole of H2O. Okay? From here, this point forward, the process is pretty much the same that we've learned before. I'm going to put moles on the bottom because I have moles on the top here. So 1 mole of H2O. I'm going to put this number on the top. Okay? Cancel units of moles and species H2O, and we have used dimensional analysis to leave ourselves only with molecules of H2O, and that's what the problem asks for. We know we probably set it up right, and we can do the math. Since we're about to do the math with exponential notation here, let me tell you something about your calculators. I don't know if you probably know this, but some of you may not, that on your calculator, when you put in a number like this, and you can try this, put this number in just the way it appears here, and hit equals, and what you're going to get is an answer that looks like this. On most calculators, you're going to get that. This is the same as this. This is a different kind of scientific notation, okay? But it means exactly the same thing. You with me? Okay? In fact, it's easier to put this in your calculator than this. If I were trying to put this in the calculator, I'd put in 6.022 times 10 up caret 23, right? How many keystrokes is that? Well, how about this? 6.022 E23. That's fewer keystrokes, right? And so it makes it a little bit easier to do. Now, if you're lucky enough to have one of these Inspire calculators, and many of you do because you're taking math classes where they kind of require that, it's really easy to put in because I put 6.022 and I've got the E button down here. I just hit it once. Boom. 23. And there's the number right there. 6.022 times 10 to the 23rd power. Okay? Now, if you don't have a TI Inspire, more than likely you're going to have to put in 6.022 and then hit kind of an up button or something. Let's see, I've got another calculator here someplace I was using earlier. Here we go. Here's a TI-84. So the TIs kind of all work the same way. So for this, I have to do 6.022, and then to get the double E, which is what my exponent button looks like, I have to hit second and then the double E to get that same thing in there. Okay? Does that make sense? So there's one more extra keystroke with most calculators. All right? But with the TI Inspire, it's a little bit faster. I like the way they did that when they set up this calculator. All right, let's do the math then. Now, you might also notice, if you want to try to simplify things, that 2 divided by 2 just gives you 1, correct? So we could cancel these out and put a 1 there, and we don't have to worry about those 2's. Sure. Sure, I'll be glad to. On which calculator? This kind of calculator? All right, I'm going to do the math with you, okay? I'm going to use this TI Inspire. Then I'll get the TI-84 over and show you how you do it on there.
Oh, it's not, you don't press into 2. No.
All right, so 2 point... All right, I'm going to put 2.00. All right, I'm going to skip over this one because I already divided the 2 by the 2 to get 1s. So multiply this times 6.022. Here's my exponent button down here. Just the double E button. Hit that and put in 23. Okay, and that's everything across the top. All right, I can go ahead. One of the nice things about TI Inspire is if I hit this close parentheses here, it's going to put that whole thing in parentheses already. Okay, can you see that? Yeah, it's lagging now for some reason. Probably got too much stuff in my computer at the moment. All right, and then divided by 2.016 and hit enter. I get this number. All right, but it does mean the same thing as this exponential notation. So it's this many molecules of H2O. Round it off properly. Find the correct answer. 5.97 times 10 to the 23rd molecules H2O. All right. Any questions about that? All right. Let's let you guys practice now. .25 times 10 to the 24th power molecules of methane are burned. What mass of carbon dioxide will be produced? You could think of it that way. this is mole to particle conversions. We went from our particle to mole conversions. We went from molecules to mass, but we had to go through this Avogadro's number conversion unit to get 91.4 grams of CO2. Now I want to talk about mole to volume conversions. And when you talk about gas volume, volume is affected by temperature a great deal. All right. I was a band parent as well as being a band geek when I was in high school. And one of my sons in band, they had this big show and a big finish at the end where they let go of all these helium balloons. So they filled up the balloons in the gymnasium in the evening before the competition. And the next day, the temperature had dropped precipitously. Okay? It was really cold the next day. So they had all these big garbage bags full of helium balloons out there in the cold, and they shrunk. Guess what the balloons did? They kind of just barely went up. Okay? So you gotta be aware of temperature and its effect on volume of gases. All right? So whenever we say that there is a mole to volume conversion, you got to specify temperature, and that's what STP is. Okay? It's not scientifically treated petroleum, which you buy in the auto parts store. It's standard temperature and pressure. Standard temperature. If you go to the auto parts store, there's a lot of products called STP. I won't get the joke, I guess. All right, that's fine. I got it. All right? I'm old, you're young. I get it. Okay. So, STP, standard temperature and pressure. And we'll get into what standard temperature and pressure more in the next unit. But standard temperature is 0 degrees C. Standard pressure is 1 atmosphere. So basically a freezing day at the beach. Okay? All right. And at standard temperature and pressure, 22.4 liters of any gas is equal to 1 mole of a gas. Atmosphere is ATM. That's a pressure unit. You know, when you put air in your tires, you usually do it in PSI here in the United States, but atmosphere is a different unit of pressure. We've got about 4 or 5 different units of pressure we use in chemistry. 22.4 liters of a gas is 1 mole of a gas. So, for this problem that I gave you for homework, okay, what it's saying is we've got everything at STP. You don't have to worry about anything except here's your quality statement to build the conversion unit for the final conversion to volume of gas. Okay? Got that? So I kind of made it easy for you. All right? Huh? No, you're going to have liters. You have to find it in liters or volume to find your percent yield. Okay? So the conversion at the end, okay, is molar volume. Molar volume. This unit right here is called molar volume.